So before we move on to our disk, let's do our background review. Let's find the electric field created by a thin ring of charge. We're going to set up our system. We're going to set up our ring so that it has a radius of A and a net charge that we're going to annotate by a lowercase q. So I'm just going to draw in the radius here. I think I'll put it right here. I know we often use R for radius. This time I'm picking A just so I can use R when I move to the disk. Okay, so there's my radius of my ring. It's got the net charge of Q. I've got my axes labeled, and I'm trying to find it somewhere above the center, so I'm definitely staying on axis here. So the first thing we do when we're trying to find an electric field due to a distribution of charge is we pick a small element of charge. A small element of our ring will just be a tiny piece of the ring. We're going to say that our element has an amount of charge called dq. And this element of charge makes an electric field at point P. This electric field is a vector. This one is going to be a little bit difficult to draw because we're trying to draw in 3 dimensions here. Maybe if I just grab my actual ring and we'll see if we can figure it out. So what my ring is supposed to be is one that's pointing out of the page like this. My dq, I'm picking a little piece, say right about here. My electric field vector comes away from it. Okay, maybe that's a little bit hard to see. Maybe if I point it like this. So if this is my dq, the electric field points straight out from that. So my dq makes an electric field at point P that points straight away from that charge, dq. So there's my little bit of electric field dE. That little bit of dE is definitely a vector because electric field is a vector, which means it's going to have components. Our dq, since it's in the back half of the ring, means it's going to point forward in the positive z direction. So the z component is going to be forward. There's dEz. The x component, it's going to be in the x direction because it comes straight out. So there's my dEx. And my y component, since I picked the top half of the ring, is going to point down. There's dEy. We know when we're finding vectors we need angles. I'm going to label this angle theta, which makes this angle theta. The distance between our charge and our point, that's what we label the distance r. Our distance along the x-axis, that's what we'll call x. Okay, now we've got our geometry all sorted out. The first thing we normally like to do is ask, is there any cancellation? Is there any symmetry here? So I'd like you to pause and ask yourself, of the 3 components, x, y, and z, do you think any of them are going to cancel to give us a net field of 0? Is there any symmetry? Okay, let's just try and show it with our little ring again. I'm going to pick 2 points on my ring on opposite sides of the ring because we know to get our net electric field we have to add up the contribution due to each little bit of charge. So I'm going to ask the little bit of charge on this side and the little bit of charge on this side, what happens to those components of field? So if I'm trying to find the field right on the axis, the electric field due to the bit of charge on this side points away from it. Due to the bit of charge on this side points away from it. So we'll see the 2 components that point left and right, they cancel, and we're left with a component that points straight out. Okay, likewise on top and bottom, one field points up, one field points down. The up and down cancel, but the forward doesn't cancel. Okay, so in terms of our ring, everything on the back half of the ring has a part of the element of let me start that sentence over. Everything on the back half of the field has a z component that points forward. Everything on the front half of the ring has a z component that points backwards, so the z's will cancel. Everything on the top half of the ring has a y component that points down. Everything on the bottom half of the ring has a y component that points up, so the y components will cancel. Everything on this ring has an x component that points forwards, so the x components do not cancel. Okay, hopefully that's clear. So to put that in a statement, we're going to say that the y component of electric field, which is going to be the sum of all the y components of the elements, equals 0. And the z component, which is the sum of the contributions in the z direction, also equals 0. And the reason that they're all equal to 0 is due to the symmetry of the ring. Okay, if we were in person, I could grab some meter sticks and hula hoops, and hopefully it would be more clear. If you're having trouble seeing it, get in touch with me and we'll just try and sort it out. That leaves us worrying about the x component. So let's see how we're going to find the x component of electric field. So we know that our x component of electric field is going to be the integral of dEx. So we get our net x component by adding up all the individual x elements. Our x element of electric field, we see that it's adjacent to our angle theta, so it's going to be given by dE times cosine theta. Okay, what do we mean by dE? dE is the element of electric field made by this little bit of charge dq. So dE is k times dq over r squared, and then we can't forget our cosine theta. Okay, what are we going to fill in for some of these things? Normally we would stick in here that dq is lambda times a length element. Let's not jump to do that just yet. Let's leave it as dq for right now. Let's worry about r. Let's worry about cosine theta. Let's get our constants in front of the integral and then see where we stand. Okay, so r is the hypotenuse of a right angled triangle where the two legs are the radius of the ring and our distance to our point. So r squared is equal to a squared plus x squared. Cosine theta is adjacent over hypotenuse, so cosine theta is equal to x over r. So if I put these things in here, my ex then is equal to the integral of k times dq times x over r squared times r. That's going to give me r cubed. R cubed so r is equal to then the square root of a squared plus x squared. R cubed will be this expression cubed. So we can fill that in for our r cubed. Okay, the next step in our integral is to take the constants out front. K is a constant, our Coulomb's constant. X is the distance between the center of the ring and the point P. That's a constant. A is the radius of the ring. That's a constant, so this whole denominator can come out front. So we have this constant times the integral of dq. Now is a good place to ask, what does an integral even mean? So the integral is the sum of all the small bits of charge as we go around the ring. If you add up each little bit of charge around the ring, what you're going to get for your answer is the net charge on the ring. So the integral of dq is just q. That gives us our x component of electric field. To finish, we were asked to find the electric field at point P. Our electric field is a vector, so we just have to finish by writing our result as a vector. So we know that it doesn't have a y component or a z component, so our net electric field is all in the x direction, which means we write the magnitude with the direction. So this is the electric field of a ring of charge with net charge q and radius a. We're going to take this result and apply it to the disk of charge to find the net electric field of a disk of charge.